So I just want to make one molecule of sodium carbonate. How many atoms do I need? Right. So hopefully you fairly quickly go that there are 2 sodium atoms in a single molecule of sodium carbonate. Okay. You could officially drag this out just like we've done every other process, which I would argue you should do. Okay. What are we being asked to solve for? Atoms of sodium. What am I given to start with? I'm given molecules of sodium carbonate. How many molecules of sodium carbonate? 1. What is the conversion between those? Because those are not the exact same thing. I need sodium carbonate molecules, and I would need atoms of sodium as a conversion factor. Where is that conversion factor found? So you're giving me a number, great. Okay. We know there's 2 and 1. Yeah. Where did that come from? Where's that information found? The subscript for the sodium is 1. I disagree with your statement. The subscript for sodium, right? It's 1.
Oh, okay.
So your statement that the subscript is 2 is a false statement.
From what we were given.
You can do better.
Okay.
Where is the information that 2 atoms of sodium are found in 1 molecule of sodium carbonate? Subscript, okay, again, a subscript next to the 1, or for sodium hydrogen carbonate, the subscript next to sodium is a 1. So you can't tell me it's just the subscript, it's the subscript found in the chemical formula. That conversion factor is found in a chemical formula. Okay? So we're trying to get very precise in our language to zero in specifically on where that information is found. Not providing general tones. For those going, well, I can't believe you're doing this. This shouldn't be a surprise. Where should we place the 2? There's a 2 right there. Where should I place it in my conversion factor? Okay, so we'll switch it. It's already placed. Where did I place the 2? In the numerator. False. Next to the atoms of sodium. Okay? We talked about this with our conversion factors. We don't place numbers in numerators or denominators. We place numbers with units. We have to be very specific in our language with where we're referencing it. Because if you start associating numbers with locations, what happens when the question changes? You're going to place the number in the location, not with the unit that it belongs to. Okay? It is a subtle change in language, but it is a language change that is significant enough that if you start placing it according to location as opposed to unit, you will make mistakes. Okay? Kind of, sort of? Cool. That gets us atoms of sodium. So for 1 molecule of sodium carbonate, we would need 2 atoms of sodium. Okay? And that might be something that we can do internally in our heads. Cool. Okay? I am officially fine with that. That question would show up as a multiple choice type question. Okay? So let's make it a little bit more difficult. What is the mass of grams of sodium to make 1 molecule of sodium carbonate? Same idea, same process. What are we being asked to solve for? Grams of sodium. Okay, what are we given to start with?
2 molecules of...
What does it say? 1 molecule of sodium carbonate. So we would argue, or I would argue, that we're given molecules of sodium carbonate and 1 of them. So now what we need to do is to look at our question and decide where do we need to go. Okay? Molecules is our measurement for molecules of sodium carbonate. Our measurement for our answer is grams in grams of sodium. Is molecules in grams the same thing? No. Okay, how about sodium carbonate and sodium?
Nope.
No. So you need both a measurement conversion and a substance conversion. If we think back to Unit 2, all of our conversions were measurements. We really didn't care about the substance. As soon as we move into chemistry, the substance becomes very, very, very important. And you need to include it in your conversions. Okay? So let's take a swing at this. Ideally, what would need to happen? I need to get rid of molecules of sodium carbonate. What do I need to bring in? Grams of sodium. Does that conversion factor exist? No. Right? So that becomes a challenge. We now have to decide, what do I want to convert? Right? Because that one doesn't exist. So saying sodium doesn't help me, because do you want grams of sodium? Okay, atoms of sodium. So we'll switch this up and go into atoms of sodium. Where's that conversion factor found? That's in our subscript from our chemical formula. Awesome. And it said what?
2 atoms of sodium.
2 atoms, 1 molecule of sodium carbonate. Okay? And here's where things are going to take a little bit of a sideways step on us. Okay? We now need to come up with the relationship between what? Atoms of sodium, which I know needs to cancel, so I'll place it in the denominator because it started in the numerator, and I would need grams of sodium in the numerator, right? Okay. Does that conversion factor exist? Sure does. Where does it exist? Okay. As was pointed out, just to, throw some salt in here, you're ahead in the reading. And because you're ahead in the reading, you should be able to tell me. Okay.
Avogadro or something like that? Or is that moles?
Isn't it Avogadro? No. Okay. The play posit starts to address this issue. Okay, and so what we're trying to do is actually tease out, why do we care about moles? Okay, so let's take a step back from this a little bit. Grams sodium is what? What is grams a measurement of? Mass. Okay, so we're looking at the mass for a particular substance, right? And then, more interesting, not just a particular substance, for a particular element. Okay, and William had an awesome little observation that I just noticed. What was that observation, William? What do you think I'm calling out?
Find its atomic mass.
Okay, the periodic table has masses on it. Okay, that was the atomic mass. That's the whole point of those mass numbers. Okay, what are the units on that mass? So if we look up sodiums, what is the mass for sodium? 22.99. So if we write that number in there, 22.99. 22.99 grams is the mass of 1 atom of sodium. So if I take a single atom of sodium, that weighs 23 grams. How much salt do you add to your food? You may add a lot, but are you adding 23 grams of it?
No.
You're adding less than an atom of sodium? Can we get less than an atom of sodium? No. So those units don't make sense. Okay? And I can agree. That's what the numbers are. But we have to be very specific with what the units are referencing. This is why units are important. Okay? The mass numbers that we talked about, if you go all the way back, it was something that I dodged and sidestepped. We never really addressed what the unit was on that. Okay? It did show up in a few cases. Okay? And it showed up in particular reference to our isotopes. Okay? What did we say the mass number was? The atomic mass is the average mass for all of the isotopes. What is the mass number? I know, you got to search way back there. Unit 1, that's hard. What particles give you mass? So we could say the electrons and protons. What was the mass of an electron, David? It was our protons plus neutrons, because the protons and neutrons were the things that had a significant mass. Electrons don't have a significant mass. Okay? If I have 1,872 electrons, I now have the mass of one proton. The largest element we've got is 118. That's a little short by 1,600 electrons. Okay? So even in our largest element with the most possible electrons possible, it's not contributing anything useful to the mass. So our mass number was our protons and neutrons. What was the mass of a proton? 1. Okay. So if I told you my mass was 2, 2 what? 1 what? AMU. What the hell's an AMU? An atomic mass unit. Literally a made-up unit so that we can say 1 is the mass of a proton. Okay? That was the point of an AMU. So we completely sidestepped and avoided an actual reasonable mass just so that we could say we had 1 for a proton. Okay? So let's actually specify this. 1 AMU I'm just going to go for it. One AMU weighs 1.6614 times 10 to the negative 24th grams. So the mass of a proton is a really, really tiny number. Understand why maybe we said it was 1? Yeah. Okay, it's a really small number. When we look at our periodic table, how we referenced it was solely by atoms. Right? So when we look at it, this isn't 22.99 grams of sodium is 1 atom of sodium. This is 22.99 AMUs of sodium. Why does that become important for us? We now have to convert AMUs of sodium into grams of sodium. How would we do that? We need a new conversion factor. That's the conversion factor that's written up there. 1 AMU, 614 times 10 to the minus 24th grams. We're a little bit crammed. I was going to go with crowded and couldn't decide between crammed and crowded. Okay. Now we could go through and determine the mass. Okay. What mass do we get? Yeah, you're the ones with calculators, not me. Okay, we'll get the mass of the sodium. So if we calculate that all out, okay, our atoms of sodium cancels, AMUs of sodiums cancel. And for our final answer, we would get 46. Keep doing that. 62-ish times 10 to the minus 24. I literally did that in my head. Come on, calculator. Don't be looking at my number like, really? Wow, I'm kind of making up numbers. What'd you get? Okay, so let's run through that again. You got 76 point what? 76.39. That's what you got. Did you multiply by 10 to the minus 24? Because I'm going to bet you didn't. Okay, everything in the denominator is 1. I'm going to bet you didn't multiply by 10 to the 24. And if we just throw in the 10 to the negative 24, it should fix that. Times 10 to the negative 23rd. Negative 23rd.
Right.
Yes. Which is this number.
Yeah.
Yes. Okay.
But in scientific notation.
But in appropriate scientific notation. And for the record, I said 62, 76.
Not that far off. Bring your head.
Okay. Not writing any numbers down. That's not horrible. Okay. Let's not worry about not scientific. What's the other word? Sig figs.
Yay.
Okay. For this case, because according to our sig figs, we really only start with 1, and that would just make this number look really, really weird. Okay. But bottom line, what we do want to say is, what is the size of that mass? Okay. Your balance in the lab room, if we go in scientific notation, measures this. So it's only like 20 points. That's not that big a deal. Your balance that measures 1 times 10 to the minus 3 costs us about $200, I think. The balance next door, 1.00 times 10 to the minus 4, is about $500. To get 10 to the minus 23, that's a lot of money. Okay? There is one allegedly that does it, because a student told me that they found one that somewhere out there, and it's something like $10 million. Okay? To minus 23. Okay? So we've got a problem here. We've got this beautiful system to look at a formula to tell us how much those pieces are. We can convert out into grams, but there's no way in hell I would ever be able to measure that mass. Okay? So that's a bit of an issue. Okay, and we could run into 20 years, great. Maybe we've got a balance to remember 800 years ago, when we're studying this, they probably didn't even have 10 to the minus 3. Okay? That stalls progress forwards until we can come up with a better way to measure that mass. And yes?
Why does it go from negative 24 to negative 23?
If we multiply these out, we would get 76. Okay? If we're at times 10 to the negative 24, if we do 1 decimal shift, we've already shifted it once, and that's why it would drop to 10 to the negative 23. Okay? So this becomes a problem. I now can't weigh things out in a reasonable amount. Okay, what would be a reasonable mass to weigh out? Gram scales. Okay? I'm at like massively small number scales. Okay, so someone went through and said, well, you know what? Fine. Okay, you're right. We're not going to be able to do that to measure out 2 atoms. Okay, I can't get that resolution. But what if I measured out 2,000 atoms? Okay. Well, if I had 2,000 atoms, well, that becomes 2,000 and 1,000. Okay. That would chip off 3 decimal places. Still not in a reasonable area. I need to chip off 23 decimal places. Okay. So instead of measuring on the scale of thousands, I'll measure on the scale of 10 to the 23rd. Okay? That's going to then negate that really, really tiny conversion between AMUs and grams. Okay? And that's kind of cool. But I would still have to run all these other conversions. Okay? So since we're in the business now of picking an arbitrary amount to measure out, I'm going to pick a very particular amount. That very particular amount is Avogadro's number. The number of particles I pick happens to be 6.022 times 10 to the 23rd atoms. Remember we said we wanted to get rid of that 10 to the power of? There it is. There's the 10 to the 23rd. It's canceling that system out. Okay? So that's pretty neat. Okay? That can help simplify the calculations. But we also have that 6.022 floating in there. Okay? And that's a little bit weird. Why would we have that in there? Okay? So if we go back with that calculation that we ran, so let's ignore that and see if I can actually do this quickly. What do we have? 1 molecule, sodium carbonate. And instead of dealing in molecules, what unit do I want to deal in? I want to deal in moles. Okay, so we're going to make a change here. It's not going to be molecules. I'm going to go up into moles. So now a very large amount. Trying to calculate this out in my head isn't working so nicely. Okay, I still want that 2 to 1. What is the measurement unit going to be now in between those two? It's going to be moles. Okay? That mole is the same number for both of those. It's that absolute weird 6.022 times 10 to the 23rd thing. Okay? That's taking care of that whole system. Right? Okay? So that cleans that up. If we now go through, we'd have moles of sodium. Okay? Before, when we used the periodic table, we had atoms of sodium, right? So the periodic table gave us that atom number, and it was 23.99 AMUs. Yeah, and 1? 22? Yeah. Right? And we said, because we were in AMUs, we had to get rid of AMUs because we didn't want AMUs. AMUs, 1 AMU, 1.66 times 10 to the minus 24 grams was 1 AMU. Like, that was awful, right? Okay? But now I have this atom mole issue. Okay? Well, how do I fix my atom mole issue? Well, atoms and moles, right? Yeah? And what's that conversion? What's the relationship between atoms and moles? 1 mole was 6.022 times 10 to the 23rd, right? Okay, so let's just pull that out. Okay, and in fact, by just pull that out, what we're going to do is get rid of all of that, because that was all just kind of our lead up into it. And, oh man, do I really have to erase it? Yeah, fudge. Okay, we're just going to pull that little thing out, 22.99. What do we say? AMUs, sodium, 1 atom of sodium. Remember all that? AMUs, sodium, grams of sodium, 6 times 10 to the negative 24th. You're like, where's the point? Well, like, why are we dealing with all of these nasty, horrible, awful numbers, right? Right? What would happen? Our atoms would cancel. Our AMUs would cancel. And the unit we'd get would be grams per mole. And be like, well, God, that's going to be an awful, ugly calculation. Well, because we see somebody punching, or I see somebody punching into a calculator, what answer do you get when you multiply that all out?
22.98.
Wait a second. Did everybody hear that? I take 22.99, I multiply it by 1.66 times 10 to the negative 24, multiply by 6.022 times 10 to the 23rd, crap ton of math, and it becomes 22.98.
Science.
Science. Man, what? That is bad.
What?
It's also science, though.
What just happened here?
You went small and big.
Okay? We had this grams of AMU thing. Okay, and we picked a random thing. We're like, boom, I'm just going to pick this number of atoms so that it gets rid of that. Okay? We didn't just pick some random number of things as scientists. We picked a number to do exactly what? To exactly cancel out the gram to AMU conversion. That is literally the point of Avogadro's number. Okay? Why is this so amazingly cool? When I now look at the periodic table and I look at the mass number for sodium at 22.99, what are the units on that number? Not quite. Because if I said 22.99 AMUs, that's also technically wrong. What did we say it was before? It was 22.99 AMUs? Is that all we wrote there? AMUs per one atom of sodium. Now the periodic table can also tell us that that same 22.99 is grams per mole for sodium. Depending at the scale that I decide to run my experiment at, I can pull a different unit off of the exact same number. Okay? That's pretty cool. That's why the periodic table's organization is neat. That's the beauty of a mole. What does that end up meaning for us as far as our calculations? A lot less work, because the whole point of the 6.022 was to do what? Get rid of that step. But at the same time that it's getting rid of the gram to AMU, what is it doing to itself? It's also canceling out, which means the whole point of a mole is to never use a mole. The whole point of that conversion is to never, ever have to deal with that nasty power of 10 again. That's the beauty of the number that was picked. Okay? That takes our formulas, and instead of being 2 sodium atoms for every 1 sodium carbonate, it can now become 2 moles of sodium for 1 mole of sodium carbonate. Okay? It is not bringing in mass, because remember, in our formula, if I ask you to build a tire or a wheel, how many wheels can you build with 500 grams of spokes? You would need a conversion factor to know how much a spoke weighs so that you could say 32 of those spokes are going to fit in there. 500 grams gives me 64 spokes, which means I can now build 2 wheels. Right? You're doing all of those conversions. The same thing is happening in chemistry. What makes it much more challenging in chemistry is how many of you have seen a spoke before? Let's try it again. How many of you have seen a bicycle? You've seen a spoke because that's the little sticky thing in the wheel. Okay? And that's okay. Maybe you just weren't aware of the terminology. That's fine. Okay? So you've seen that. You've experienced it. How many of you have seen a molecule of sodium carbonate? Okay? We can draw them. Okay? So that when we draw out you know what I'm referring to, right? That's Greg. You're all like, dude, your picture. He's smiling. Greg's always smiling. I'm the one that's frowning, right? They're your teachers for the class. Okay? Yes, we can draw a picture, but that picture requires a translation within your brain. Sometimes that translation makes sense. Sometimes it doesn't. Okay? With chemistry, you don't have that real world to deal with, so you're literally creating a fictitious image to represent something you've never seen and trusting that it somehow works. Okay? There's a reason why chemistry was considered magic for a very long time. Okay? What's that?
It sounds like creative writing. Fictitious world.
Yeah.
Well, that's
Right?
still.
But what makes chemistry so much more real than that fictitious world of creative writing is that the fake things that we're doing with these weird images actually come true. We can predict stuff. That's what makes chemistry powerful. That's what makes drawing these random images are like, why the hell are you doing that? So cool. Is that we can use that to predict what something else is going to do. That's phenomenal. Right? But the human brain takes a long time to deal with that because you're literally creating a fictitious system and being like, why would this ever work? Holy crap, it does. Right? When do you start to actually believe that your fictitious system was useful? After you see the results, which means you're relying on experience to trust that. If this is your first chemistry class, you haven't had that experience. Arguably, if it's your second chemistry class, you haven't had that experience. You need a significant amount of experience behind that protocol or that fictitious world to actually trust and believe that it works. Okay? So at this point, you pretty much have to trust somebody else's experience. Okay? Which, believe it or not, you've already done with virtually every decision you've made in your life. Okay? This is no different in that respect. Okay? So, let's take a look at some conversions. Okay, these ones are a bit obnoxious in my opinion because these are all going to require the usage of that mole conversion. Okay? How many oxygen atoms are in 0.240 moles of oxygen? Okay, so you guys want to try it on your own first, or should we walk through it? You think we should just walk through it? Okay.
No,
We'll walk through it
I
to...
think they need some active something.
Okay, we'll walk through this one, but we're going to walk through it together. I will only start to put things down when you give me hints as to what to do.
As long as it's not David.
Okay? Isn't it 0.24 moles? Okay. How many oxygen atoms are in 0.24 moles? Okay. If our answer is 0.24 moles of oxygen, wouldn't we be done? What are we looking for? Oxygen atoms. Is a mole oxygen atoms? No, it's a large number of oxygen atoms. Okay? So it's two different systems. It's not a direct translation. Okay? So what am I looking for? I'm looking for oxygen atoms. Our general format has been to put the measurement first, followed by the substance. So what I'm going to do is flip it, and instead of writing oxygen atoms, I'm going to write atoms of oxygen. Yeah? Okay, do you want to make any abbreviations? Okay. So there was a suggestion that we should write O. There's also a suggestion that we should write O2. Which should we write?
You need to take the times 2 into calculation.
It's asking for what? Oxygen atoms. What is O2? 2 oxygen atoms, which means if we're going to solve for atoms of O2, is that a true statement? No. We have to be very careful with our language. Remember, what we're talking about with oxygen is a diatomic molecule. Okay? And yes, O2, when I refer to oxygen gas, it is absolutely O2. When did I say we should not look at O2 to represent oxygen? Because believe it or not, I did actually tell you that when we talked about diatomic elements. Okay. When do we reference oxygen as O2 versus O? when it says it. Okay? If it's explicitly stated, then it's O. If it's not explicitly stated, it's O2. What is the explicit statement you're looking for? Atoms of oxygen. The question literally tells you atoms of oxygen, which means the symbol you need to be writing would be
Oh.
atoms of O. Okay?
If you say diatomic atoms, that's like atoms.
Yes. Saying the word diatomic atoms is like saying atom
It
atoms.
should trigger you that something's not right.
Okay? Because an atom is a single atom. Diatomic is two atoms. It doesn't make sense to refer to a diatomic species as an atom because by definition is more than one. What were we given to start with? I'm going to complain about the 0.24. Let's try that again. We're given moles of O2. How many moles of O2? Good follow-up.
3-1.
Okay. Now what? So we're hearing a suggestion for convert moles to atoms. I would argue no. First, you need to address, do you need to do a conversion?
Yes, because we have to get to atoms of oxygen. Molar.
Yes, we do need to do a conversion. What conversion do we need to do? Okay, dividing by 2 is a mathematical system. I want units. This is an English class. I want to see some language. This is substance that we're given is O2. The substance I'm solving for is O. So what do I need to do? A substance conversion. Okay. Is that all I need to do is just convert the substance? Why not? Moles ending at atoms. We have a measurement conversion and a substance conversion. You have to address both. If you only address one, you're wrong. Okay? This is why it's useful to write that information down and do that check backwards and forwards. Okay? So, which one do you want to deal with? Measurement or substance? Substance first. Okay. What do I want in the denominator? O2. Why? So that it cancels. What do I want in the numerator? O. Where do I find a substance conversion? A substance conversion is found in a chemical formula. What are the measurements in a chemical formula? It could absolutely be atoms, okay? And it's really up to you to decide, okay? So we could relate atoms of oxygen to atoms of O2? Not moles. Molecules of O2. Okay? It's the single substance. What is that numbers that go with that? Molecule of O2. This conversion is pretty cool because what did it bring in? Atoms of oxygen. That's fantastic. I wanted that. Okay, so that's good. But at the same time, it brought in molecules of O2. Did I want that? No. So I've actually made a bigger mess of things, right? Okay. So I now need to do another conversion. I have to cancel out some units. What units do I want to cancel out? Okay. What do I want to relate that molecules of O2 to? Okay. Why do I want to relate it to moles of O2? I also have to cancel out the moles of O2. So I could recognize that that moles of O2 needs to show up in the denominator so that I can get that long distance canceling. I could also look at the question and be like, was I just given molecules of O2? Nope, which means I'm going to have to do a conversion. I have to find something to relate that to. Where's that conversion found? in the mole conversion. Okay? So William is suggesting, quite bravely, the mole conversion tells us the relationship between moles and molecules. Mole conversion tells us atoms. If you go to the store and buy a dozen, what are you buying? I can go to the store and just buy 12.
Sure can.
Yep.
Did someone say of wine? Maybe. I go to the store and I buy a dozen. Donuts. Okay? What if I go to the farmer and ask for a dozen? What is he going to give me? Eggs. Okay? A dozen is the same thing as a mole. It's a large number. A large number of what?
Unit.
Of any substance, of anything. So when we write this conversion up here, 1 mole is equal to 6.022 times 10 to the 23rd atoms, it's a bit misleading. That really what that thing is saying is that 1 mole of atoms equals 6.022 times 10 to the 23rd atoms. 1 dozen eggs is equal to 1 dozen eggs, 12 eggs. Okay? Sometimes it doesn't have to be a weird number. Okay? Why did we invent a dozen?
Because it's used commonly.
Why is it used like a dozen is the same thing as a mole. Why do I need to invent a dozen? Why can't I just go, I'm going to buy 12 eggs? Farmers can't count that high. Okay? Someone clearly watched the Play Pause It video. Okay? At least one person. That's fantastic. Okay? The human brain has a hard time with numbers, which is why scientific notation, we get things down to the ones place. We don't want to exceed the number 10 because we have 10 fingers. Okay? So by going up to a dozen, 12 things, I'm like, well, how do I count to that? Okay, I can't represent that unless I take off my shoe. And that added time takes too much extra time in the finance market, so I don't want to do that. So we invent the concept of a dozen to simplify things. The exact same thing is happening with moles. All we're trying to do is simplify things. The problem is that what we're simplifying is what? An atomic substance. And what did we say about the atomic substance? You can't see it. So what did we do to represent that atomic substance? We made up a picture for it. So we're inventing a large number to represent a fictitious thing that we've never seen. We're making something up to explain something that we made up. For those of you wondering, I'm pretty sure that's what gets you thrown in the loony bin. Okay? You're dealing with a lot of made-up things. This can make it challenging. Okay? The power of it and why we don't all end up in the loony bin, more than once, okay, is that we can use that to predict. I can now determine how much product should be made. Okay? That's pretty phenomenally cool. Okay? So we have to kind of trust and rely on that. So when we go up to this conversion factor, relating it as atoms is probably a bad idea, because that's like saying a dozen can only be eggs. But when I go to the donut shop, it's donuts. So a dozen is representing what? 12 things, not units. Because if I go to buy a dozen grams, that doesn't work. Grams is a measurement, okay, not a counting feature. So what we're talking about is a substance. Okay? Are atoms a substance? Yeah. Are molecules? Are elephants? Donuts? Okay? Straw? Yeah. All of those things are things that we can append to the end here. So instead of saying atoms, I could instead say things. Molecules would work for this specific case. Okay? 1 mole of things is 6.022 times 10 to the 23rd things. Okay? The thing conversion allows me to now apply that to anything. Okay? So now what do? We can drop our conversion number in there. Where do we place the numbers? 1 mole is molecules. What happens with our units? Moles of O2 cancel. Molecules of O2 cancel. What unit would I have? Atoms of oxygen. What was I solving for? Atoms of oxygen. What can I do now? Now I can do the math and just multiply the things out. Kind of make sense?
Did everybody write that out? As he did? Sure did. Any notes right now? Sure did.
So, some conclusions is we now have ways that we can use that conversion factor. The point of that conversion factor is that we can convert the mass on our periodic table, instead of being AMUs per atom, can now be grams per mole. Grams is a measure of mass. Another way that we can conjugate the noun moles would be molar to make it an adjective. Sweet. And we've got a molar mass. Okay? So, there you go. Your turn. What is the molar mass of copper 2 nitrite? Oh, who's coming through the door? Okay, yep, super clever. Okay, so what we're bringing in is now a whole nother layer of difficulty on Unit 2. In Unit 2, you were given your conversions. In Unit 3, you have to know where to find the conversions and how to use them. So again, the point of Unit 2 was not use conversions, but was to figure out a process that you could rely on so that when the units became fictitious pictures, you could trust the process to get you to an answer. Okay? That was our whole point behind that division of labor, if you will. So let's go ahead and take a look at this question. What are we being asked to solve for? We're being asked for the grams of copper 2 nitrite. Does anybody want to write out grams copper 2 nitrite? Okay, that's a lot of words, a lot of letters. It'd be nice if I had a shorthand for that. Okay, one shorthand, that could work. Okay, the problem with that looks like cyanide, looks like carbon and nitrogen, not copper 2 nitrite. So if you start inventing your own shorthand, it's okay, but the problem is that you'll likely overlap everybody else's accepted shorthand with yours, and that's going to mess things up. Okay? So our accepted shorthand is to come up with the proper formula for this. This question becomes difficult because now not only are you being expected to come up with a conversion, but you also have to know nomenclature so that you can write down the proper formula. Okay? So in that nomenclature, you're responsible for knowing that copper is Cu. Nitrite. Are you responsible for knowing that one?
Yes.
You're responsible for nitrate. You're not responsible for nitrite. Okay? What's that? You want to do your 8 thing, that's on you. Okay? So I would argue you could ask very quickly the question, what the hell is nitrite? And if you had asked, I would have told you, it is NO2. Even if you didn't ask, when I walked around and I saw it, I pointed it out, that you did nitrate, not nitrite. The next part that you're responsible for is making sure that you have the proper amount of both of these. Copper is a +2, says what? Says the Roman numeral 2 next to the copper. Nitrite is a -1. Why? It just is. That's one you would have to know. That is one that I would also, if you'd been like, I don't know nitrite, I would have been like, it's NO2 -1. Is that formula, or does that formula correctly balance out the charges?
No.
So what do we need? We would put in parentheses and a 2 at the very end. Right? This now allows us to specify the exact amount of each of those pieces. Why is that important? What are we being asked to solve for? Grams. Okay? If I change the amount of elements, is that going to change the mass? Yes. So it is very important to know how many elements are actually in my system. Okay, what was I given to start with? I'm going to complain about the 0.532. Moles of the copper nitrite. Okay, and we were given 0.0532 moles of copper nitrite. Look across the equation. What do you see? Grams and moles have changed. Has the substance changed? No. So we could theoretically do this in one step. Okay? That one step, what has to happen? The moles of the copper to nitrite has to show up where in my conversion? In the denominator, so that it can cancel with the moles that were already there. What do I want to show up in the numerator? Grams of copper to nitrite. I now have to decide, does that conversion factor exist? Is there a conversion factor that relates mass and moles for a substance? Okay. Yes, that does exist. How do I know that? Because I've had the experience to acknowledge that that conversion factor exists and that somebody pointed out that it does exist. Where does it exist? So good terms, atomic mass can be used as molar mass. That's kind of in the giant red box. Where is that information found? Periodic table. Okay. Is that just a quick insert of a number? Nope. I actually have to go through and add it all up. I'd have to look up copper. Copper is what? That is the mass of what kind of copper? So a couple people saying, what is fair. What is 63.55 the mass of? What type of copper is that the mass of?
Most common average.
The most common average.
I threw that in last.
It is the average of all isotopes of copper. Are we being told that we're looking at a specific isotope of copper?
Yes. No.
Okay. So a couple people said yes. What specific isotope are you referencing?
2.
Copper 2. 2 changes what?
1 stinking electron.
Changes the number of electrons. Isotope changes the number of neutrons. Copper 2 is not an isotope, it's an ion. Right? So the other statement that could come out will be, well, copper 63.55 is for all isotopes. This is copper 2. Well, what's the difference between all isotopes of copper and copper 2?
That's an ion.
This is an ion. So again, what's that difference?
Not that much.
1 stinking electron.
Careful. 2 electrons. Okay? Well, so let's subtract the mass of 2 electrons.
There we go. Done.
63.55. The electrons don't contribute to the mass. Okay, so we don't have to worry about changing the electrons, changing our number. So that is now the mass of 1 copper. How many coppers are in copper 2 nitrite? 1. Why do we know that? The subscript from our chemical formula. If we didn't know our chemical formula, we might have put in 2 of them. You have to be careful with your nomenclature to apply it. What else is in our formula? Nitrogen. Nitrogen has a mass of 14.01. How many nitrogens went into this? 2. There's 1 nitrogen for a nitrite, but there's 2 nitrites. So I would do 14.01 times 2 plus 16 for our oxygen. If we wanted to get really nitpicky with sig figs, we could say 16.00. Y times 4. There's 2 in nitrite. We have 2 nitrites. We add all of those numbers up and we get the magic number of 100, and I'm going to have to do an equals this way, 155.7, you said? 5.7. What are the units? Grams per mole. Where does the 155.57 go? Does not go in the numerator. It goes next to the grams. Now what happens? The moles cancel. What would we have as a unit? Grams of copper nitrite. What can we do? Now do the math. Okay? Lots of intricate steps that you have to follow through and move through very meticulously. The instant you start skipping steps, you're begging for mistakes to come in. Okay? This is why we pushed in Unit 1, careful balancing of those terms and charges. In Unit 2, careful balancing of structures and nomenclature and everything else. Unit 3 is now the sum total of everything. All of it comes in. Okay? Make sense? Okay.
For you, Unit 3 is really, there's a lot of practicing the knowledge.
Unit 3 is just practice.
Again, so it's paralleling what we're doing with the children's book, where
Yeah.
in both classes we have accumulated a certain amount of knowledge and mechanisms that we can use systematically so that now when we go to practice this thing called writing or practice this thing called chemistry, we have that background knowledge that we can apply. So if there are any gaps on the back end, you need to go back and fill those gaps.
And it will come back to haunt you. Right? So constantly be reviewing backwards as well as going forwards. Right? Should we go through and do this one?
Yeah, 4 minutes, let's go.
4 minutes, let's go. It sounded like a race. What do we want for an answer? Grams of lead. What was that given to start with? Oh, and I just made one of my cardinal mistakes. Okay. Wrote the number first. Remember, our units should go first. Atoms of lead, grams of lead. Are those the same thing?
No.
What changed? Letters changed. The measurement changed, right? Atoms, grams. Okay? Both of those are lead. I just realized a big issue here. What's the big issue going to be? Is there a conversion factor that relates grams to atoms?
Yes.
Periodic table gives you. So periodic table gives you 2 potential conversion factors. I want to hear what those 2 conversion factors are. AMUs per atom, absolutely, and grams per mole. Do we have a conversion factor between grams and atoms? No. That conversion factor doesn't exist, which means we're going to have to do at least 2 conversions. Right? Why is that a problem? I don't have enough space. Okay? This is one of the reasons why when we talk about it at the beginning, We said to do our numbers really far to the left to give us lots of space to go through and solve. Right? What do I know needs to happen to the atoms of lead? They need to cancel out. Okay, what do I want to convert the atoms of lead to? I can go to AMUs of lead, that's fine. Okay, where do I find that? It's on our periodic table, and it says 0.2. Okay, what would happen? Atoms cancel out. And I'd have AMUs of lead and grams of lead. Does that conversion factor exist?
AMU to mole, so we should
2.55 times 10 to the 23rd atoms of lead. So now the suggestion is going to atoms was a bad idea. So maybe let's go to grams of lead. So grams of lead, what would we relate grams of lead to? Get some confidence behind it. Moles of lead. Okay. That would be 207.2 grams of lead is 1 mole of lead. No units canceled. That kind of sucks. What would I need to have happen? Moles of lead would need to cancel, so that could be placed in the numerator. What could be placed in the denominator? Atoms of lead. Is there a conversion factor between moles and atoms? What is that conversion factor? Avogadro's number, which you're required to memorize. For those of you saying 1.66, hold your horses. 1 mole, 6.022 times 10 to the 23rd atoms of lead. Okay, we still have this hanging blue that we're like, damn, we don't know that conversion between grams and AMUs. Somebody with a calculator, take 1 divided by 6.022 times 10 to the 23rd. What is 1 divided by 6.022 times 10 to the 23rd? 1.661 times 10 to the negative 24th grams is 1 AMU. Avogadro's number was invented literally to cancel out the gram to AMU conversion. They're inverses of each other. Okay? So you can solve it either direction. This is one of the things that makes conversions tricky. Right? And I want to reiterate that. They become tricky because there's multiple paths that you can take to go through and solve. The solve that we may walk through in class may not be the path that immediately jumped out at you. That does not make your path wrong. Okay? What it does mean is that you should verify your path. How? Check with somebody else. Okay? You can't check on a test, which means what do you need to do in preparation for the test? Practice it so that you trust all paths that you could possibly take. Okay? With that, we're done with class today.